In the previous two videos, we considered how vertical asymptotes and holes in the graph can arise when we're graphing rational expressions. Now we're going to consider how horizontal asymptotes arise. To think about horizontal asymptotes, we have to think about how the function behaves as x becomes a very large positive number and as x becomes a very large negative number, or as x moves towards positive infinity and as x moves towards negative infinity. Graphically, that means we're thinking about moving far to the right as x becomes a very large positive number and far to the left as x becomes a very large negative number. So here's an example. The function h of x is equal to x plus 1 over x squared minus 1. Now, drawing on what you've learned already, you might want to simplify this function by factoring the denominator, which factors to x plus 1 times x minus 1, and canceling the common x plus 1 factor that's in the numerator and the denominator. Now, we know from what we've learned of restrictions that x cannot be equal to negative 1 and x cannot be equal to positive 1. Those would both be restrictions on the function. Now, what's happening when x is equal to positive 1? When x is equal to positive 1, the denominator only becomes 0. So that is going to be a vertical asymptote. Now, when x is equal to negative 1, both the numerator and the denominator are going to become equal to 0. So that means that x is equal to negative 1 is the x-coordinate of a hole. So that's a little review of what we've looked at already. Now let's think about the horizontal asymptotes that exist in this graph. And to do that, we need to think about what's happening as x becomes a very large positive and as x becomes a very large negative number. So first of all, you might notice that because x is squared in the denominator and not squared in the numerator, as x becomes large and positive, this x squared is going to become much larger and much more positive than just the x in the numerator, because we're multiplying x by itself. A large positive number multiplied by itself is larger than just the large positive number without any multiplication. Now here, what I've done is I've made a table of values with x getting larger and larger and worked out the y values that correspond. And I've done this with the original unfactored, uncancelled function, although you could also have done it with the factored and cancelled version. Notice that when x is equal to 1, we get y is undefined. That's our vertical asymptote. Also notice that as x gets more and more positive, as we go down here, the y values get smaller and smaller and smaller and approach 0, but never get there. So as x is going towards positive infinity, what we see is that y, or h of x, is approaching 0. Now, let's go in the opposite direction. As x approaches negative infinity, well, you start from 0, and I've plotted some, or I've given some values here. When x is equal to negative 1, notice we get 0 over 0. That's indeterminate. That's the location of our hole. As you go further and further to the left, as x becomes more and more negative, you see that the values are getting smaller and smaller. They're staying negative, but the absolute value of these is getting smaller. They're getting closer and closer to 0. So again, as x is going to negative infinity, now we're seeing that h of x, again, is going towards 0. Don't get confused by the opposite order of the arrows. I just wanted to show or emphasize that when x is going to negative infinity, you're moving to the left on the graph. So what that looks like is this. As you move off to the right, as x goes towards positive infinity, the function is getting closer and closer to 0. And as x goes to negative infinity, you see the function getting closer and closer to 0 as well in its y values. You see also the vertical asymptote and the hole that we referred to before. We'll continue talking about horizontal asymptotes in the next video.